Hello everyone, welcome to this new series on computer architecture. Throughout this series we're going to cover the basics of computer architecture. So for the first topic I'd like to start with data representation. Whenever we say data in case of computer architecture, we think of some form of storage, right? So the type of storage that we're considering here is basically registers. So with reference to registers, what we can say is basically the data that are found in the registers of digital computers can be categorized into three major categories. The first is numbers, that is used in arithmetic computations. The second is letters of alphabets, that is used in data processing, alphabets. And the third are some discrete symbols that we'll see sometimes later. So these are the three major data categories that we have that are present in the registers. Now let's start with something called a number system. And the first term that I would like to introduce here in case of number system is a radix. So what exactly is a radix? Let's say we basically use a decimal number system in our case, right? So when we say 50.5, what this actually means in terms of radix is 5 into 10 to the power 1 plus 0 into 10 to the power 0 plus 5 into 10 to the power minus 1. Now if you find the product of each of these three terms and then add it, you basically get 50.5 here. Notice the term 10 being used in each of these three computations. Now this number 10 basically in case of a decimal number system is called a radix. So what I can say is in case of a decimal number system the radix is 10. This is also called a base. So what about in case of binary? In case of a binary number system, the radix or the base used is 2. Let's say we'll take an example of representing a binary number here called 101101. We all know this transformation. If we want to convert this particular binary number into a decimal number, then what we do is we use a base or radix of 2. So 1 into 2 plus 0 into 2 plus 1 into 2 plus 1 into 2 plus 0 into 2 plus 1 into 2 to the power 0, 1, 2, 3, 4, 5. Now if you sum this up, 32 plus 0 plus 8 plus 4 plus 0 plus 1, and this is equal to 45. So you see that the base we've used in case of a binary number is 2 and the base we've used in case of decimal number is 10, and that itself is called a radix. Now let's move on to binary codes. So what are binary codes? So a binary code is actually a group of n bit that assume up to 2 to the power n distinct combinations of zeros and ones. So a group of n bits that assumes up to 2 to the power n distinct combinations of 0 and 1. Let's say we want to represent a set of 4 elements, then what we can do is we can represent this set of four elements using a group of 2 elements here. So what I can do is I can use 0 0 0 1 1 0 and 1 1 to represent a set of 4 elements. Similarly, when representing a set of 8 elements, what I can do is I can use a 3-bit code. So basically 0 0 0 would mean 0, 0 0 1 would mean 1, 0 1 0 would mean 2, 0 1 1 would mean 3, 0 1 sorry 1 0 0 1 0 1 1 1 0 and finally 1 1 1. So these will means 4 5 6 and 7, a total of 8 elements. So this is a binary code. So what is a BCD then? BCD is also called a binary coded decimal. So to represent any decimal number, what we do in BCD is use a group of n bits. So suppose we use 4 bits to represent this number. Then what we do to represent 0 is 0 0 0 0. So the decimal equivalent or the BCD equivalent of the decimal number 0 is 0 0 0 0. Similarly, for 7, what we do, so this is 1 2 4 8, right? So 4 plus 2 plus 1 is 7. So this can be written as 0 1 1 1. Similarly, if you want to represent a number 10, what we can do is we can write 8, there will be no 4, there will be 1, and then there will be 0. So 8 plus 2 is basically 10. If we see this conversion like we did earlier, we can use the radix or base of power 2 and then check if our conversion is correct or not. 2 3, so 2 to the power 3 is 8 plus 0 plus 2 plus 0 is equal to 10. So this can be written as 0 0 0 1 0 0 1 1 1 can be written as 0 0 0 1, 2 can be written as 0 0 1 0, and so on. So this is a binary coded decimal. Sometimes we get confused with BCD and binary values. So let's take a decimal number of 99. Let's say this is written in decimal form. The binary equivalent of this number 99 will be 1 1 0 0 0 1 1 1. But the BCD equivalent, where we take 4 bits to represent a digit, so there will be 1 2 3 4 5 6 7 8 bits here, which means the first 9 will be represented as 1 0 0 1 and the second 9 will be represented as 1 0 0 1. So you see the binary as well as the BCD values, they're not exactly the same for a particular number, but they are different in terms of their representations. Now we'll move on to alphanumeric representations. So what exactly are alphanumeric representations? So many applications of digital computers requires the handling of data that consists not only the numbers but also of letters of alphabets and some certain special characters. So alphanumeric character set is a set of elements that includes an alphanumeric character set is a set of elements that includes 10 digits from 0 to 9, 26 letters of alphabets, if we count both upper and lowercase, it's going to be 52, and also a number of special symbols like $, plus, equals to, etc. So number of special characters. So alphanumeric representation or alphanumeric character set is a set of elements that contains 10 digits, basically from 0 to 9, 26 letter of alphabets, all in lowercase right now, but if you also consider uppercase, this is going to be 52 letter of alphabets and some special characters. So such a set contains between 32 and 64 elements if only the uppercase letters are included, or between 64 and 120 elements if both uppercase and lowercase letters are included. So for the ones where only the uppercase letters are included, it will require 6 bits to be represented, because the maximum number is 64, right? So 2 to the power 6 equals to 64, so it can fit inside 6 bits. And if both uppercase and lowercase bits are included, or like uppercase and lowercase elements are included, the maximum goes up to 128 elements, which will require 7 bits to be represented. Now we move on to complements. Complements are actually very essential in terms of digital computers. Well, I'd like to give an example. Suppose an addition of 2 BCD values or 2 binary values is like very easy. Let's say we want to add 1001 and 101011. So addition of these 2 values can be done or can be implemented using a full adder circuit. So it is very easy. But when we talk about subtraction, now the subtraction becomes complicated, because it's not very straightforward in comparison to the addition. So in this case, what we do is we basically use complements of our subtracting value, basically use the 2's complement of our subtracting value, and then finally add those values and then find out the result of the subtraction. So the complements are actually very essential here. The complements are used in the digital computers for simplifying the subtraction operation and for logical manipulation. So there are 2 types of complement for each base system: the R's complement and R minus 1's complement. So when the value of the base R is substituted, the 2 types are referred to as 2's complement or 1's complement here. And both of these are very important in case of digital computers for subtraction operation or for simplifying the subtraction operation, as well as for logical manipulation.